Thanks very much. It's a great honor to give not just this talk, but the Maxwell lecture, because Maxwell was always one of my heroes. He was actually a mathematics professor, but is known for some work he did in physics, namely figuring out the laws that govern electromagnetism and using them to predict the speed of light. What better could you do than that? So my talk is going to be about some unsolved mysteries of fundamental physics, and I'll try to teach you a tiny bit of physics in the process, because you sort of need to know where we are to know what we don't know. So I mean something rather specific by fundamental physics. I mean the search for a small set of laws which, at least in principle, although probably not so easily in practice, determine everything that we can calculate about the universe. So this is the dream of reductionism, that dream that you could write on a postcard some magical equation from which you could derive, the melting point of lead or the size of the average snowflake or anything like that, if you're good enough at calculating. This isn't always practical. We know a lot now about the difficulties with reductionism. We know, for example, that we'll never be able to predict with certainty whether it's going to rain in Cambridge. Well, certainly not within a week, maybe not even tomorrow. I don't know where the weather reports stand now, because of the complexity of the motions of air and water vapor. To build a computer that could simulate the system accurately enough to predict what it does, the computer would basically have to be as big as the system itself, approximately. And it would take about as long to run as the weather actually takes. So fundamental physics is a limited pursuit. I'm not saying that it's the best kind of physics. I'm not saying that physics is the best kind of science, but there's something specially attractive about the search for fundamental laws. And so the questions arise: where do we stand right now in searching for these laws? And what do we know and what don't we know? What are the mysteries? So the most fundamental question of all, as you probably already know, is why? So there are a lot of people who say that science doesn't address why questions. It doesn't say why things happen. It just says what happens. And there's definitely some truth to that. So for example, I think Newton really pushed that attitude when he wrote down his laws of classical mechanics and the inverse square law governing gravity. He said in some Latin phrase that I'm not making any hypotheses, by which he meant that he was going to resist the temptation to say why these laws were true. And it's very important that scientists have the right to do that. So for example, when Gell-Mann invented the idea of quarks and posited that protons and neutrons were each made out of 3 quarks, if somebody had said, come on, you have to tell me why this is the case before I'm going to let you proceed with this theory. Why in the world should protons be made of 3 quarks? I think it's crucial that Gell-Mann had the right to do what he probably would have done, which is to say, sorry, I don't know why, I don't care why, really. I'm much more interested in figuring out the consequences of this theory than why. And yet, science often moves forward by asking why questions. So the key thing about why questions is to know when it's good to ask them and when it's less productive to ask them. Of course, children haven't been trained to resist asking why questions at certain points, so they would start pretty much anywhere and ask why. And it's very interesting to think about how these networks of why questions lead on to further questions. So one very obvious question is, why is the sky blue? If you're in the middle of a jungle, quite commonly it would be the only blue thing there is that you see. And so a standard answer now is, well, more than light of other colors, blue light is scattered in various directions by the Earth's atmosphere as it's coming in from the sun. And so you especially see, like when the sun is setting, it's going through lots of atmosphere. The sun looks very red because most of the blue light has been scattered, and what's left is more of the red type of light, whereas the scattered light is what you see on a sunny day in the rest of the sky. But then, of course, every why question, when answered, gives the potential for one or more further why questions. So the next question is, why is blue light scattered more? And then a standard answer might be, well, because blue light has a shorter wavelength than other kinds of light, most other kinds of light. Already here there's some subtleties. Anyone who's really studied this question about why the sky is blue will be able to like poke holes in things I'm saying. Of course, violet light has an even shorter wavelength than blue light. So if this is all there was to it, the sky should be violet, not blue. But the point is there's more to it than that. The sun produces different amount of light at different frequencies, and it doesn't put out enough violet light to have violet be the dominant thing you see. So it's a more complicated situation that I'm letting on here. But then you can ask, okay, why does blue light have a shorter wavelength? Well, now this would make a physicist start getting nervous. This isn't really the kind of question they want to answer. So they'd say maybe like, no reason, we just happen to call the visible light with short wavelengths blue. That's just sort of the definition of blue. So if you've ever tried explaining physics to non-physicists, you will often encounter this sort of situation where they're asking you questions, and some of the questions you feel like, oh good, that's a great question, I know the answer to that. And then sometimes the questions will veer off in a direction that makes you intensely uncomfortable because it's not the kind of question you know the answer to, or maybe not even the kind of question you think there should be an answer to. So like the person could persist and say, yeah, okay, you call it blue, but why does light with these short wavelengths actually look blue? It's like this slide here is supposed to be, I don't know how well it's projecting in my screen here. It looks just sky blue. And at that point, you would have to say, I don't know, that's not a physics question. In fact, no one really even knows what kind of question that is. It could be a psychology question, but it's sort of so tough that they say, no, sorry, that's a philosophy question. And so don't make fun of philosophers for never solving these questions of philosophy. The problem is their situation is that whenever there's a question that no one has a clue as to how to answer, they say it's philosophy. So of course we can't answer the philosophy questions, right? So there's the whole idea of qualia. Is there such a thing as blueness, the blueness of blue? It looks very apparent to me. If you ask me to describe it, I can't do it. I could just say, well, it looks blue. So anyway, forget this. This is not the way we want to go. So a better direction for physics is, so why does light with short wavelengths scatter more than with long wavelengths? And one first answer is, well, what's really going on is the light's going through the air, and it's actually hitting individual molecules. It's molecules of air, oxygen and nitrogen mainly, that scatter the light. And the light gets scattered with an intensity proportional to 1 over the 4th power of the wavelength. So light with shorter wavelengths scatters much more. And then, of course, the next question is, well, why? Why does light do that anyway? And then you can say, well, it's nothing particular about nitrogen and oxygen. It's just a general fact about electromagnetism, that electromagnetic waves scatter off particles that are much smaller than the wavelength of the particle with an intensity that's proportional to 1 over the 4th power of the wavelength. When the wavelength gets to be so small that it's about the same size as the particle, then it gets more complicated. But visible light is much bigger than atoms. And so this approximation of thinking of the particles is much smaller than the wavelength is valid, and you get this famous 1 over the 4th power law, which is called Raleigh's scattering. And this is a graph of how much of the light gets scattered as a function of its wavelength. But then, of course, the next question is, well, why 1 over the wavelength to the 4th power? Why not the 9th power or the 3rd power? And now this is a kind of question that physicists will get very happy about, and they'll start I could spend the whole rest of the lecture talking about that, but I won't. So I won't do the calculation here, but Raleigh showed this in 1871, and he actually showed it in a rather simple way using what's called dimensional analysis. So in physics, you have to keep your units straight. You can't just say 2. If you're talking about how heavy something is, you have to say 2 kilograms. And by keeping track of the units and making sure that they work out properly, that is, you have equations that have the same units on both sides, you can figure out lots of stuff. And you can, in particular, figure out this 1 over the wavelength to the 4th law from just some fairly simple assumptions. And the main assumptions are, one is that space is 3-dimensional. There's 3 x, y, and z coordinates. And the other is that the energy density, the amount of energy per cubic centimeter of an electromagnetic wave, is proportional to the square of the amplitude. So if you changed either of those facts, you'd get a different law. And in particular, for example, if space was just 2-dimensional, if we all lived in flat land instead of 3-dimensional space, there would be a different law. The intensity would go like 1 over the wavelength cubed. So this is a lot of fun for physicists because you could do calculations and you can think about what would happen if you change different things and get different answers. So this is a kind of why question that a physicist would consider very productive. But of course, every why question leads to another one. So the next question could be, well, why is space 3-dimensional? And that is a hard one. No one has a clue, really. Well, there's ideas, but that's too hard. Nobody, I would say, knows the answer to that one. So I'll stop there. So there are lots of really interesting questions in physics that right now they just seem too hard for us. And usually when you start out thinking about physics, those are the first ones you think about, and those are the ones you'll never know the answer to. So you have to get interested in things that are a little easier. Why is space 3-dimensional? Why is time 1-dimensional? We do know by calculations what it would be like if time were 2-dimensional, those of us who care about such things. And it would be really weird, okay? It would be really different. We might not even think of calling it time. It would be so different. But you can nonetheless, you can say what it would be like, but we don't know why time is 1-dimensional. Another question that's very interesting in fundamental physics is really, are there any fundamental laws? We're looking around for these fundamental laws of physics. We've been looking and looking and looking and never finding them. Maybe there aren't any fundamental laws of physics. Maybe there's only a series of better and better approximate laws. There's no guarantee on the universe that says there's going to be some fundamental laws. So that's an interesting question, which I doubt I will ever know the answer to. And then, of course, a slightly more practical question is, what are the fundamental laws? Well, if there are fundamental laws, what are they? That's what we spend a lot of time digging away at, but we don't know the answer to. So we learn to sort of cut our expectations down and try to tackle questions that are a little bit easier. But it's important to realize that even these questions that I just listed, that may seem hopelessly hard to answer, we should never, I think, completely give up hope. Because there are a lot of questions that once looked way too hard to answer that have actually been answered. And I'll just pick one. Why is time so darn different from space? So we've got 3 coordinates that we call space. We've got one that's called time. They're incredibly different, right? So you can go back to your dormitory, but you can't go back to last Wednesday. There's all sorts of things that are different. But there's an answer to this question, which Einstein came up with when he invented special relativity. This is an answer that applies in special relativity. It gets fancier in general relativity, but it's the same basic answer. The answer is that back when you learned to calculate distances using coordinates, you learned about the Pythagorean theorem that said that the distance from here to there is the change in x squared plus the change in y squared, and then take the square root at the end. And in 3 dimensions, it would work the same way. You'd have the change in x squared, the change in y squared, and the change in z squared is the distance squared. But if you include time, Einstein realized you can include time in this formula, but it comes with a minus sign. You get minus the change in time squared plus the change in x squared plus the change in y squared plus the change in z squared is the square of something that we don't usually call distance anymore. We call it interval. It's a kind of unification of the notion of the distance in space and the distance in time, but with this funny minus sign. And I'm working in units where the speed of light is equal to 1, so that time shows up on an equal footing with space, more or less. But that minus sign is the answer to the question. Everything comes from that darn minus sign. You can do calculations in physics, in special relativity, and you can see all the stuff about our world that makes time being different from space, all arising from that darn minus sign. It turns out it's not so much the minus sign as the relative minus sign. I could use a different convention, and people often do, where I put minus signs on all three of the space guys, and I put a plus sign on the dt squared, delta t squared, and that would also make time act the way it does. So really what matters is just that it comes in with a different sign. So that of course, would again be potentially the start of a long lecture where I explain why that's really, how that really works. I mean, this is a cryptic answer that needs expounding to be clear. But this is great. It really is the answer as far as I'm concerned. So that's, of course, why Einstein is a sort of well-known guy. He could do stuff like that. So what it means for me is that it's very hard to know for sure which questions we'll answer next and which ones are hopeless. But it certainly helps to know where we stand now before you can make a guess as to which questions we'll answer now. So let me just give you a quick tour of where we stand in fundamental physics. We have two best theories of fundamental physics today, one of which describes all the forces and all the particles except for gravity, and one of which describes gravity. The standard model describes three kinds of forces: electromagnetic, which is the thing that's making the light in this room, the weak force, and the strong force, which you only notice when you do experiments with atomic nuclei or subatomic particles. And it describes them all using quantum mechanics. It's easy to do experiments with these kind of forces on very tiny distance scales, and on very small distance scales, quantum mechanics becomes incredibly important because you learn that what you thought were just point particles are actually wave functions. They're blurry things. General relativity only talks about gravity and how gravity is affected by matter, but it doesn't give a detailed description of matter. And gravity is very hard to do experiments on small distance scales because it takes something pretty big, like a planet, to generate a significant amount of gravity. So we don't know, we haven't done any experiments, any serious experiments connecting general relativity and quantum mechanics because it's just too hard for us right now. And so general relativity does not take quantum mechanics into account. So right now, our picture of the universe is sort of split in this horrible way that we have one theory for everything except gravity, and we understand how it works with quantum mechanics, and then something else for gravity, but ignoring quantum mechanics. No one in physics that I know of thinks that this is the last word in the situation. In fact, if you try to, you could say like, well, maybe gravity doesn't care about quantum mechanics. Maybe the right theory of gravity doesn't involve quantum mechanics. But it turns out if you try to do that, you get in even more trouble. It's bad. It does not work. So we know that general relativity should be unified with the others, at least insofar as they should all be talked about using quantum mechanics. But we don't know how. There's been a lot of work trying to do that, but we don't really know how these two fit together. So let me talk a bit about the standard model first. So I'll talk about them separately. So the standard model describes particles and their interactions, and it uses special relativity, and it uses quantum mechanics. And so some of the first particles to be thought about this way were the electron, which are those E's there, and the photon, the carrier of light, which is written gamma, because sometimes some kinds of light is called gamma rays. And here at left, we see one kind of thing that can happen. And at right, we see something else that can happen. But the basic thing that can happen is always the same. It's just an electron is moving along, and it emits a photon. Or the same picture could be used for other things. You could also say an electron comes along and it absorbs a photon. We're basically reading the picture from bottom to top here, but depending on the slant of that horizontal line, you could say that somebody is emitting or absorbing a photon. And even to make it even more fun, you notice that these electrons lines have little arrows on them, which are sort of going forwards in time, but you notice some of them are going backwards in time, like this one over here at the left of the right-hand picture. That's called an antiparticle. That's a positron, the opposite of an electron. And here what's happening is that an electron and a positron are colliding, turning into light, turning into a photon, and then that photon is breaking back into an electron and a positron again. Those things really do happen. And the beauty of this is that these two pictures are just the same picture, just turned around. So the same theory predicts these various processes in a unified kind of way. But now the standard model has a bunch of particles. And here they are. Here are all of them. There are particles that carry forces, one of which I mentioned, the photon, carries the electromagnetic force. So like if you have a magnet and it's attracting a piece of iron, there are actually photons involved doing that. The weak nuclear force is carried by particles called the W and the Z. There's actually a positively charged W and a negatively charged one. The strong force is, which holds, for example, a proton together. Protons are very hard to bust, so we think they're held together by an extremely powerful force, and it's carried by particles which are jokingly called the gluons, and there are actually 8 of them, 8 different kinds of them for some nice mathematical reason. And then there are particles that constitute matter, and the strange, mysterious thing about them is they come in 3 generations, each generation being very similar to the other generations. The first generation is sort of the one that has all the particles that are in this room in large quantities. The electron is in the first generation. I'll skip the next guy for a second. The down quark and the up quark are the 2 kinds of quarks that make up protons and neutrons. For example, a proton is 2 ups and a down. A neutron is 2 downs and an up. And then there's one ghostly thing called the electron neutrino, nu sub e there. That is a particle that's very hard to detect and yet has been detected. And for example, when a neutron decays into a proton, it will emit, among other things, it will emit an anti-neutrino of the electron type. So they're involved, but they're very hard to detect. And then the really weird thing is that there's a second generation of particles that's very much like the first one, and a third. And the main difference between these 3 generations is just the masses of these particles. So for that mu thing is a muon. It's a lot like an electron, but it's almost exactly 207 times heavier. When they first discovered it, they weren't expecting it. And this physicist I. Rabi said, "Who ordered that?" They were looking around for particles that would help solve the problems that they were dealing with. This one showed up. It's like a waiter brings you a particle on a tray that was not what you ordered. And we still don't know really why there are these other generations. But they're definitely there. And then finally, there's one more, which you may have heard about, called the Higgs boson, which was the last of these to be discovered. And it interacts with all the rest that have mass. All the particles that have mass get their mass by interacting with the Higgs boson. That's what there is. And they interact in various ways. And this is just like a cute little chart for how they interact, where we draw a blue line between 2 particles if there's some interaction between them. And so, for example, the Higgs there is interacting with all the particles that have mass. And it has mass, so it interacts with itself. The W and Z bosons have mass, so it's interacting with them. The photon does not have mass, so there's no line between the Higgs and the photon. And the gluons are also massless. The gluons interact only with the quarks and with themselves. So the gluons mainly hold quarks together to form things like protons and neutrons and stranger particles of the same ilk. The other kinds of particles forming matter are called leptons. So they're like the electron and the electron neutrino are called leptons. They don't interact with the gluon. So they don't feel the strong force, but they do feel the weak force. So there's a line from them down to these weak particles, the W plus minus and the Z, and so on. So you have to write down a formula that says exactly how all these particles interact with all these other particles, and it's pretty long and complicated because it must involve all of these things, and there's no underlying principle from which we can derive all this stuff at present. It's just stuff that we've observed to be true. So in fact, you need 25 fundamental constants, 25 numbers, to describe the strengths of these various interactions. These are numbers that are dimensionless constants. Like one of them, it's called the fine structure constant, tells you how strong the electromagnetic force is. It's 1 over 137.0 blah, blah, blah. We have no idea why it's that. 22 of these 25 numbers involve the Higgs boson because it's interacting with lots of other things and giving them mass. That's why why it was such a big deal to actually really discover for sure the Higgs boson. We knew it was essential, but it was good to actually see the darn thing. So this should make you have all sorts of questions. You should be able to ask me like at least a month's worth of questions about that last slide. I'll just ask like a few of the ones that instantly come to mind. Like, why are there 3 forces in this picture? Why not 5? Why not just 1? We don't know. We have no idea. Why does each generation include 2 leptons and 2 quarks? There's this strange thing that the quarks are a lot like the leptons, but they're also not, right? So the quarks feel the strong force, the leptons don't, but they still, in each generation, you get 2 quarks and 2 leptons, and there are a lot of other similarities between them that are a little fancier to describe. Why are there 3 generations? Why not just 1? It would be so much simpler if there was just 1. Why do these various numbers I mentioned have the values they do? So there is definitely progress on some of these questions. There are attempts to unify these 3 forces into a single force, and those are called grand unified theories. And some grand unified theories offer what seem to me pretty tempting answers to the first 2 questions. In other words, there's a theory called the SO10 grand unified theory in which you can see that you're going to get 3 forces from it, even though it starts out being one single unified force. And even better, you can see that each generation of particles is going to have 2 leptons and 2 quarks in quite a bit of detail. So quarks are weird. Quarks have charges like 2/3 and -1/3. Whereas an electron has charge -1. But this grand unified theory says why they've got to have those weird charges. It fits in a certain way, and you just can't change it. It's got to be that way if the theory is true. There are problems with this theory, which is why not everyone believes it yet. But there's so much that seems to work. It's hard to escape the impression that it's on the right track. On the other hand, the third question about why are there 3 generations, I don't personally believe there's any really good theory about that. Of course, there are theories about it. Theorists, that's their job, is to make up theories of stuff like this. So, there are at least 100 theories of it. But that doesn't mean that I'm convinced of any of them. And the fourth one, why do the constants have the values they do? That's so hard that a lot of physicists have just said, forget it. We're never going to answer that. Don't ask it. If you want to know more about these grand unified theories, it was very nice that you just happened to mention a paper that I wrote with a grad student of mine with the title, The Algebra of Grand Unified Theories. If you know, some physics and some math, you could take a look at this, and it's our attempt to explain in relatively simple terms. You may disagree when you look at the paper, relatively simple terms, what's going on here. So I think there's definitely some progress in this on these questions, but I wouldn't say that they're answered. And in fact, it seems easier to make progress on certain other puzzles. So for example, what's up with these neutrinos? The neutrinos are weird, and they've always been weird. So at first people thought they were just like made up for bookkeeping purposes, that energy wouldn't be conserved unless some mysterious particle was shooting out of a neutron when it decayed. But then they found them, they actually detected them. Very hard to detect them, but they did. But then our opinions about them keep sort of shifting as we learn more and more about them. For a long time, people thought they were massless. They have very small mass. But now we know that they do have a non-zero mass. I guess if you're really technical, we know that there's at most one that's massless, because we can mainly measure mass differences, or actually differences of squares of masses. So there could be one that's massless, but we don't think that. They probably all have a mass. And then the other thing people learned when they saw that about 1/3 as many electron neutrinos were coming out of the sun as we expected, was that these guys can turn into each other. And so those electron neutrinos are actually turning into muon neutrinos and tau neutrinos before they reach us. And we can now do experiments on Earth where you make neutrinos of one kind over here, and you'll look for neutrinos of another kind over here, and you see, yeah, we're getting them now when you turn this on. When you turn it off, they're not there. So they're turning from one kind into another as they zip through space. And all this, to describe how all this works, actually eats up 10 of those 25 constants I mentioned in the standard model. They're all about talking about how neutrinos are doing these things, and they're all due to its interaction with the Higgs. So it's sort of mysterious already, but what's more mysterious is that the standard model may not be really fitting the data we see. There are anomalies, weird things in the data. So here's the kind of thing that physicists do. You build an 800-ton spherical tank of mineral oil. You bombard it with muon neutrinos that you make from a particle accelerator that's 500 meters away. And you watch it very carefully for 16 years with all these photomultiplier detectors here. All those little yellow dots are things that detect photons that are formed when, for example, a neutrino is absorbed by one of the atoms in your mineral oil, or if for other reasons. So you have to sift your way through the noise. You carefully watch this, and you discover, or they discovered at this experiment, which is called Minimoon, that if you hit it with muon neutrinos, if you make muon neutrinos 500 meters away, that you seem to be detecting electron neutrinos in this detector, this big vat of mineral oil. And what's weird about it is that they've only gone 500 meters, and so they've had to have turned from one kind into another pretty quickly, and we have, the standard model makes predictions for how long it takes for them to do that, and that they shouldn't be able to do it that fast. Other experiments would suggest that they should have to go a lot further before this happens. So in other words, the experiment is not fitting the standard model, apparently. And so people are very interested in this. An earlier experiment had detected the same effect, and that's why they replicated it in a different way at Minimoon. So it could be that there's a fourth kind of neutrino that's making things more complicated, or it could be that the experiments are wrong in some way, and I would give that a pretty hefty probability, because there's, as I said, there's various other sources of little photons in your tank of mineral oil, and you have to be very careful to correct for these other sources of noise. Or it could be something else. So next, they're going to do MicroBoone. I think this is sort of a jokey terminology. It's not exactly small. It's 170 tons of liquid argon, a noble gas, and they're going to replicate the experiment with higher sensitivity and see if this effect is real. So stay tuned. In another 5 or 10 years, we'll know. It takes a long time to do these experiments because it's very hard to detect neutrinos. You have to wait. Every so often, blink, you get one. Okay, so that's an example of something that we're going to actually find out in our lifetime, at least if we're young enough. Let's switch over to the other side, the gravity side. General relativity is much simpler than the standard model. It's mind-blowing, but it's simple in comparison. It says that if you have any freely falling object, it will trace out a path that's as straight as possible, but space-time itself is curved. So it's like if you're like walking around on a sphere, you could be trying to go as straight as possible, but you may like wind up back where you started from, or something funny like that, and you blame it on the Earth being not flat. But matter is what's making space-time be curved, and the meat of general relativity is this equation called Einstein's equation, which is usually written in a fancy way, but I'm trying to write it in a simpler way that says the same thing. And it tells you how matter curves space-time. And it says, if you've got imagine like a little ball of particles. So like imagine like you're floating around in the space station and you like spill your Nestle coffee powder. And there's this little ball of coffee grounds floating freely, only, not feeling any force except gravity. And the gravity of each other as well. And the rate at which this volume begins to shrink of this little ball of particles, if it starts out that they're initially at rest relative to each other, so the ball starts out not expanding or shrinking, but then it starts accelerating inwards due to its own gravity, and the rate at which its volume begins to shrink is proportional to, well, the volume, but also the energy density at the ball, in the middle of the ball, plus the sum of the pressures in all three directions. You may be used to situations like air where the pressure is the same in all three directions, but like if I step on a book, there's pressure more this way than the other directions. So pressure really, you have to say which direction you're talking about pressure. And so as an equation, you'd say the second time derivative of the volume of the ball divided by the volume of the ball initially at time 0 is minus 1/2 the energy density plus the pressure in the three different directions, and I'm using units to make some constants equal 1. So basically it tells you exactly how matter curves space in such a way that all these guys trying to go straight nonetheless start converging in on each other if the energy density and the pressure are positive. So from that one principle and tons of work, you can derive Newton's law of gravity, believe it or not, in the limit when you're only studying slowly moving objects, much slower than the speed of light, and weak gravitational fields. But you can also figure out the formulas for black holes, gravitational waves, and the expansion of the universe. And so I want to just sort of rapidly sketch out how the expansion of the universe works. And if you want to know more, you could type the meaning of Einstein's equation into the all-knowing Google, and you'll be led to my paper where I start. Ted Bunn and I start with this formulation of Einstein equations, which, believe me, is tons simpler than the usual one, and try to just use that to figure out well-known stuff about gravity, well-known that you read in a relativity textbook, that is. So for a long time, people thought the story was that in intergalactic space, there's not much stuff there, so the pressure is negligible. So we'll only, except in the very early universe when things were really scrunched up. So we'll just throw away those pressure terms in the last equation and just write this simplified one where all that matters is energy density, rho. Now remember, E equals mc squared, so you can convert mass density into energy density if you prefer to think about mass density. So if you imagine, I was talking about a small ball of particles, but now the universe is very large. So I can imagine a, quote, small ball containing our galaxy and a few hundred other galaxies, and apply this equation to it. And we can simplify it a little bit because the the volume is proportional to the radius cubed, and the mass of all the galaxies in this ball will be the density rho times the volume cubed, I guess times 4 pi over 3. So you can get rid of volume and get rid of volume and write it in terms of radius, and you get an equation like this. You have to do some algebra to do that. And this says that the second time derivative of the radius of this ball of galaxies is proportional to 1 over, or minus 1 over the r squared. So it's like a 1 over r squared force law, which is just what you'd get for studying a rock thrown up from the Earth. If you threw it up so high that you actually noticed that gravity was weaker far away, because gravity gets weaker like 1 over r squared. So what we know right away is that this expanding universe is going to collapse back down on itself unless it's expanding fast enough to exceed escape velocity, unless it's expanding fast enough. So there are 3 basic possibilities for what the universe can do in this simple model, which is of course oversimplified in some ways, but it's widely studied. So one is that it could expand, starting from very small radius, expand and shrink down. This radius is not the radius of the whole universe. It's the radius of any particular ball of galaxies in the universe. So they could spread out and then crunch back down. This is called a big bang over here at left. This would be called a big crunch over here at right. For a while, people thought that was really a serious option. It's mathematically a serious option. But it turns out that we're more like in the open scenario where the universe keeps on expanding forever. And right at the brink of the two, there's a critical situation where it manages to expand forever, but sort of just barely. So those are the 3 possibilities. And that was what people were very interested in the 50s and 60s and 70s, which is it? And the answer seemed to be that the universe was going to expand forever. But then, when they got to be much better at measuring things about galaxies using all these wonderful satellites we have, they found that the universe is expanding faster and faster. So the big question is why? What's making the expansion accelerate? One possibility would be that the vacuum has negative pressure. That, believe it or not, is the most popular explanation. But if so, why? And if not, what else is going on? Maybe our laws of gravity are wrong. But the most popular option, it's called dark energy. You've probably heard that. What it really means is that the vacuum has negative pressure and actually positive energy. And you just need a tiny amount of this dark energy to match what we see. But we don't know why it's there, if it's there. And there are a lot of other mysteries about gravity, which are hard to solve, like the one I mentioned before. How do we combine it or reconcile it, at least, with a standard model? What really happened at the Big Bang? Some people will say, like, there was nothing before the Big Bang. But we don't know that. We don't know. We know stuff that happened shortly after the Big Bang, even like microseconds after the Big Bang. We have a pretty good picture of what was going on, that I believe, but not at the Big Bang. So that's a big puzzle. Similarly, sort of in the other side of things, what really happens to stuff that falls into black holes? Hawking came up with convincing calculations that say that black holes should eventually radiate away, evaporate away. But there are a lot of questions about that people love to argue about. And while we're at it, no point in thinking small here. What's the ultimate fate of the universe? Is it really just going to keep on expanding? If so, it's going to be, given the physics we know now, it could be sort of boring in a way. It will turn out eventually that it will, if we just use the theories we have now and act like we know what's going on, we'll eventually reach a state where every atom is completely far away from every other atom. And so nothing much fun can happen, which is sad. But maybe that's the way it is. Another one, why is the future so different than the past? Well, if you have this cosmology which starts at the Big Bang and then expands forever, then of course the future is incredibly different than the past. And you might just say, that's it. That's just all there is. That's the way it is. And then we'll try to lay every other difference between the future and the past on that. So if you ask most physicists, like, how come you can remember the past but not the future? They will try to tell you a story, which I think is a pretty convincing story, that it's ultimately due to this Big Bang versus eventual eternal expansion of the universe. That's a long story to get into that, obviously. It's not obvious that they're connected, but we think they are. But these are hard puzzles. Easier ones are the ones where you have data coming in, new measurements, and dark matter is the buzzword for this thing that I'm talking about here, which is it seems that most of the matter in the universe is some invisible sort of matter that's not like any of the kind of matter we know about. There's lots of evidence that something like this is true. Galaxies are rotating much faster than can be explained by all the understood forms of mass. The heavier something is, the more the gravity there is, the faster things should be orbiting. But galaxies are not spinning the way we think they should be unless there's extra stuff. Galaxies don't even form at all in our simulations of galaxy formation unless we have this extra stuff, which is called cold dark matter, in the sense that it's like cool enough that it will collapse down and help seed galaxy formation. The fluctuations in the microwave background radiation, the leftover glow from the Big Bang, fit a model that has cold dark matter and not a model without. So most physicists believe that this dark matter is real. It simultaneously explains a lot of mysterious things, but then the question is, what is this stuff? And luckily, we're getting new data from astronomy quite a bit, quite rapidly, that may shed new light on this. Also, people are just doing experiments to look for weird kind of particles. So these enormous vats of argon or mineral oil that we could use to detect neutrinos, you could also build similar detectors or even the same detectors to detect other kinds of particles that hardly ever interact with anything. And so people are using the same experiments and also other experiments to look for dark matter particles, and so far no success at all, which makes people wonder if maybe there's some other explanation of all this mystery. So I gave a talk sort of similar to this around 1995, and one thing that strikes me is how little my talk has changed since then, although I made it different in some ways on purpose. But basically, by the 1980s, theorists had worked out the standard model. General relativity had been worked out much earlier. And so they could have told the story of general relativity in the standard model that I did way back then. And they were very happy that they'd gotten this far. And they thought, we must be pretty close to figuring everything out. We just have to figure out how the standard model and general relativity fit together, which may be just something that we could do just like sitting down and thinking about it. And they guessed that they were pretty close to the final theory of fundamental physics. And around the 1980s is when people had invented string theory, which has a nice ability to get gravity and other forces into a single picture. But it has the not so nice ability of saying that's extra feature that it says that space-time is 10-dimensional and that every particle that we see has another particle that we don't see of the exact same mass, and so on and so on. So there are lots of unfortunate features of string theory. So they decided first to unify the forces other than gravity. So I'm going back a little bit, come up with these grand unified theories, and then unify them with gravity. And that was where people tried theories like string theory. And they hoped that the mathematical aesthetics, that is coming up with a really beautiful theory, combined with what we already knew, could quickly finish the job. But that just did not happen. That's not what has happened since the 1980s. What has happened since the 1980s is that we found the Higgs boson, and you may have read these exciting accounts in the newspapers, but physicists were all going, oh no, that's just what we knew what we're going to see. We were hoping to find something different or more other particles, but no, nothing new from the Large Hadron Collider yet, although I was talking to a student and she says that they're discovering some interesting anomalies with B mesons, so maybe we'll find something. But they haven't yet, let's say. And the other things that have happened are that we've gotten more and more information about the mystery of dark matter, but we still don't know what it is. We've definitely detected gravitational waves. So last time when I gave this talk in 1995, we hadn't detected gravitational waves, so that still was sort of interesting, although everyone knew that they were going to happen because Einstein was right, you know. So it's been a sort of frustrating period, I'd say an extremely frustrating period in physics, partially because it had been such rapid progress from 1900 to 1980. Einstein wrote a paper arguing that atoms existed in his youth. So back when he was young, they weren't even sure that atoms existed. By the time he died, we were studying subatomic particles and making up the Standard Model. It's incredible change during that period. It's just not happening that fast now. So I think it's experiments that we need to look at. And luckily, experiments keep on revealing new clues. We don't know what to do with these clues yet, but they keep accumulating. So just last week, a paper came out on results from an experiment called ANITA, the Antarctic Impulse Transient Antenna. It's this big thing which they actually lift up on a balloon, and it looks for neutrinos, but it looks for neutrinos in an interesting way. So this is like 1 to 4 kilometers thick of ice in Antarctica. Some neutrinos skim the Earth's surface, the neutrinos coming from outer space due to wild, crazy things happening with stars far away and black holes far away. And some of these neutrinos will skim through the ice, like this big nu here. And because they're actually going faster than the speed of light in ice, they produce radiation called Cherenkov radiation, which is sort of like a sonic boom, but for light. And when some of that radiation is in the form of radio waves, and then some of it gets refracted when it comes up into the air, and then ANITA floating up in the air there will detect them. So it can detect neutrinos in this indirect way by the radio waves that they produce. But they seem to have, in the last bunch of years, seen 2 incredibly high energy neutrinos coming up, actually must have gone through the ground, not just going through the ice, but coming up from a steeper angle. And these super high energy neutrinos actually do interact with matter fairly strongly, so we don't think they could make it through the ground. Neutrinos that are low energy can go through anything for a long, long time. They can go through a light year of lead without any trouble. But these are super high energy neutrinos, and they interact a lot, so they should not have been able to do this. So in other words, we're seeing some things happen that we don't see how they could happen if the Standard Model is all there is. Of course, we could just be like neglecting something with some clever way that things could happen. But that got people excited, and that's the kind of thing that we have to keep looking for. Little cracks in the armor of our existing theories. There are plenty of them. We need to find more of them, and someday someone, or some group of people, no doubt, is going to put together these clues and make us take a little step closer towards answering these why questions that I'm talking about. Thanks.